So the topic of this video is going to be how chemical reactions occur, which is a step-by-step description or a chemical story of each step. You remember that most steps in chemical reactions involve either one molecule or two. So mechanism is a familiar word. It has meanings such as how a clock works is called its mechanism. Okay, and we're going to illustrate some of the ideas here with a very important mechanism, and that is how ozone is made in the upper atmosphere, the stratosphere, and how it is removed, and how that process protects us from ultraviolet light or not, depending on how it's removed. Okay, so the first thing to do is to talk about how ozone is made. And so what happens? That ozone, which has a Lewis structure with a double bond, ultraviolet light of a certain wavelength, and this wavelength is about 240 nanometers. So this is hard UV. It's really quite a bit shorter wavelength than the top of the range of the violet, which is about 400 nanometers. Okay, and I'm going to write each oxygen atom explicitly. You might be able to just understand it if you just write 2 O dot. So that's the first step. So this protects us from ultraviolet light of this particular wavelength. All right, that's good. Okay, then ozone is generated by an oxygen atom hitting an oxygen molecule to form an O3 molecule called ozone. All right, and so that's going to be nice. In order to get the overall reaction to balance out, this second oxygen atom will also hit an oxygen molecule. So I'm just going to write this step twice. It's the same step. It's just that it happens many, many times inside a situation where there's any oxygen atoms, any oxygen molecules. If they ever collide, then if the energy is sufficient to overcome the activation energy, then you'll get an ozone molecule. Okay, so the overall reaction is just the sum of these 3 steps. Okay, so there are 3 O2 molecules here. And these are called reactants. There are 2 ozone molecules here. These are called products. And there's an extra molecule or atom here that's involved that's neither a reactant nor a product. It's something that is made in one step and removed in the other step. And so this is called an intermediate. So the key that you have an intermediate, it does not appear in the overall balanced reaction, and it's not anything there at the beginning or at the end. It's made and in the process used up to create something else. Okay, so that is the 3 terms we use for this particular mechanism. Now, how does ozone protect us? Well, ozone protects us through another mechanism. So O3 is hit by light of about 300 nanometers. So not as high energy as this light. So it protects us from a different frequency of UV. So there are bands of UV called UVA, B, and C. And so ozone protects us from one band. Molecular oxygen protects us from another band. And so when ozone absorbs light, you get the oxygen molecule plus the oxygen atom. Okay, and we're going to write this twice to get the overall balanced reaction to occur. Okay, and so, you know, there's Avogadro or many, many moles of ozone. So, you know, just this happens multiple times. But then if an atom meets another O atom, which is rare, then you can terminate this. That's to say, remove the oxygen radicals and get molecular oxygen. So let's look at this overall reaction here. It's 2O3 or absorbed light of 300 nanometers and form 3 O2s, which is just the reverse of this reaction. So now we can see how ozone and oxygen are involved in this cycle where ozone is made and ozone is destroyed, and in the process it protects us from UV light of 2 different wavelengths. Okay, so that's all well and good. All right, and the intermediates again are the oxygen atom. Okay, so now we have to talk about a phenomenon called ozone depletion. Okay, so this process depletes ozone, but in the process of doing so, it protects us from UV. Well, if there's something that removes ozone, then there's no ozone to absorb this UV, and then the UV gets down to us, and we have more likely skin cancers and other sorts of effects from UV light. Okay, so the mechanism we're going to talk about is chlorofluorocarbon. Now, chlorofluorocarbon is just a carbon with chlorines and fluorines. And so we'll just pick an example where there's a carbon atom with 2 chlorines, 2 fluorines. Now, these were thought to be ideal materials when inert materials were required in industrial processes. So, for example, freon won't break down or chemically react, but if it does get into the atmosphere, it turns out that, well, maybe there's a photochemical reaction that happens high up in the atmosphere. So there was a famous scientist called Sherry Rowland who was investigating these sorts of reactions. And then, so it turns out that CFCs also absorb UV light. Different frequencies, depends on what the actual compound is. You get chlorine atom plus the other fragment. And it's the other fragment that might further fall apart into more chlorine atoms and more fluorine atoms. But we're more concerned with what happens with this chlorine atom. Okay, so chlorine atom plus ozone gives you ClO and O2. Okay, so chlorine atom will get rid of an ozone molecule without absorption of UV light. Okay, you might say, okay, well, maybe it absorbed 1 photon to make chlorine atom, so maybe that's okay. But it turns out that it's much worse than that. Okay, now the next step in the mechanism is that 2 of these ClOs can combine to form a molecule. There. All right, and then this molecule can fall apart. Okay, and then this fragment can fall apart as well. Okay, so let's look and see all the steps that are involved. Chlorine atom takes an ozone to this chlorine monoxide radical. Okay, you need 2 of these, and so what I'm going to do is I'm going to write the first step twice in order to make the overall reaction cancel out the intermediates and other substances. So let's assume that we'll have 2 chlorine atoms generated from 2 different CFCs. We're just repeating the first step twice. Okay, so let's look at the overall reaction of this one. All right, so the easiest thing to do maybe is identify intermediates. Okay, there's an intermediate, which I'm going to outline in pink here, because it's made in those 2 steps and it's removed in this step. Okay, so that's an intermediate. All right. This molecule is an intermediate. Cl2O2 is an intermediate. All right, and then this fraction here, ClOO, ClOO. Is also an intermediate. So we've got 3 intermediates in this chemical reaction. So now let's look at the overall reaction. Ozone, ozone. So there are 2 ozones. 3 O2s. Hey, it's the exact same reaction. So ozone normally takes UV and does this. This does not require UV except to generate the chlorine atom in the beginning. Okay. The bad news is that I'm going to highlight something here. It's not an intermediate because without chlorine atom, then none of this would occur this way. So this is a catalyst. So a catalyst is something you add at the beginning of the reaction to alter the mechanism, to speed it up, and it gets regenerated at the end. So it's not like an intermediate, which is not there at the beginning. It's formed by your mechanism and then consumed. This is added, participates, and then gets regenerated. And in the process, it lowers the activation barriers and makes the reaction go much faster. So the chlorine atom is a catalyst. So the problem with the catalyst is the chlorine atoms that get generated here in these 2 steps can go hit some more ozones and continue to remove ozone. So 1 chlorine atom can remove thousands of ozone molecules. That's why it's particularly bad for ozone depletion.